Hello and good evening. My name is Jamal Saldogo, and this is my CSTR design equation for my CBE final project. So here we go. So firstly, we have the question that we need to solve. It states that component A is fed into the inlet stream 1 and component B is fed into inlet stream 2. The rate of reaction of species A is KO, CA 0.5, CB 1.5, and KO would be 0.31 liters per grad mole times seconds in this case. The reaction has the following characteristics, which we will be using to make our image shortly. The system is at a constant density of 0.98 grams per centimeter. The volumetric flow rate of steam 1 is 12 liters per second. The mass flow rate of outlet stream is 63.3 kilograms per second. Entering concentration of A is 1.9 gram moles per liter. Entering concentration of B is 2.7 gram moles per liter. And the conversion of species A is 0.54 and species B is 0.74. So now that we have all these input values over here that we'll be using, the big question would be, what is the required volume in liters? So right here, we're gonna write an equation for volume in terms of volume. So V equals FAO XA over RA. And we're gonna go through what these all mean. So FAO right here would be the molar flow rate of A entering. XA in this case would literally just be the conversion of A. So this value right here, 0.54, would be the case for X of A, which we'll input in our final step. And furthermore, R of A would be the rate of consumption of A at the exit. And it is gram moles per liter times seconds. And there you go. So here's what we're starting out with. And we will shortly go through each and every step, about 7 steps to solve this equation right here and ultimately bring the volume down to determine the volume. Firstly, let's make an image just to have a visualization of what is going on in the reactor. So we have one output right here, and we have 2 inputs into the CSTR. And we'll have stream 1 here and stream 2 here. And remember, constant density, as stated above here, is gonna stay at 0.98 grams per centimeter cubed. So let's keep that in mind. And we know that VO, or the entering concentration, the volumetric flow rate of stream 1 is 12 liters per second. And for stream 2, CAO of stream 2, which is the molar flow rate, would be 1.9 grab moles per liter. So there we go. So we have our volumetric flow rate for stream 1, and for the second stream, we have the entering concentration of A. And then right here at the side, we'll have XA, which is 0.54, and XB, which is 0.74, as stated above by species B and species A. And finally, we have the outlet stream. And its mass flow rate, which equals 63.3 kilograms per second. So here's our visualization. And this will just help us image and imagine what is going to go on. And we're looking for the volume of the CSTR ultimately. Without further ado, let's go on to step 1. So, a lot of moving parts. For step 1, we're just going to find the FAO, which is the molar flow rate of A entering. So, let's do that. So yes, the inlet concentration of A, or CaO, is equal to 1.9 gram moles per liter. And the volumetric flow rate of stream 1, Q1, equals 12 liters per second. So using these numbers, we will determine FAO by doing CaO multiplied by Q1, which equals the same as 1.9 times 12, which equals 22.8 gram moles per second. So in this case, FAO equals 22.8 G mole per S. Moving on to step 2. Step 2 would literally just be finding C of A. And the equation for C of A would be C of A equals CaO 1 minus XA. So we just input the values for it, 1.9 as we have gone over in this step, in the previous step. 1 minus X of A, which is 0.54. And that would equal 0.847 gram moles per liter. Step 3, we are looking for Q out, which is the volumetric flow rate. So the equation for Q out would equal M over P, or the outlet mass flow rate in this case, which is 63.3 kilograms per second, and P right here would be the density, which is 980 grams per liter. So we literally just divide these two, but keeping in mind that as kilograms, we will do 63,300 grams to turn it into grams per second. And then we would put the same thing, now that they have the same level of units, it would be 980 grams per liter, which would equal 64.59 liters per second. So this would be Q out right here. So FBO, the equation for that, which is the same as Q2, flow rate of the second stream, would straight be Q2 equals Q out minus Q1. Now we have both these values. We have Q out, which equals 64.59, for Q out, minus Q of 1, which is 12. 64.59 liters per second versus minus 12 liters per second equals 52.59 liters per second. So now that we have Q2, we can find FBO, which equals 2.7 multiplied by 52.59 liters per second. Okay, so in doing that calculation, we will end up with 141.993 gram moles per second for FBO right over here. Okay, so that is the end of step 4. We're moving on to step 5, finding CB, which would be in this equation as follows: CBO 1 minus X of B equals the answer in gram moles per liter. So CBO, as we learned previously, would be 2.7. 1 minus X of B, which is at a constant rate of 0.74. And that would equal 0.702 gram moles per liter. For number 6, we're starting to put everything all together. But firstly, we have to find R of A, which is our bottom value in our big equation. So R of A, to determine R of A, you got to do KO multiplied by CA 0.5 times CB 1.5. And we will remind ourselves of the values that we have on the side. KO would be 0.31. CA would be 0.874 to the 0.5 power times 0.702, which would be CB, to the 1.5 power. So, in doing all this math, first of all, we could do 0.874, which would be 0.9349. And then 0.72 would be the same thing as saying 0.702 multiplied by the square root of 0.702, because this would be 0.5, and this would be 1. 1 times 0.5, 1 plus 0.5, 1.5 right here for the exponent over here. Anyways, and getting that, you would get a number of 0.5884. So here we got 0.9349, 0.5984, and we multiply these by 0.31 to get our answer, which would be around 0.1707 gram moles per liter times seconds. Finally, we are at our final step, which would be plugging everything back into the equation to determine the volume. So we know what all of these values are. It would be to plug all of them in. So it would be 22.8 for FAO multiplied by 0.54 at a constant rate for XA, of course, divided by R of A, which we just got in the last problem, which is 0.1707. And in doing this math, we'll come to the final answer of 72.1 liters. So then again, coming back to our target, what is the required volume in liters? V equals 72.1 liters. Thank you very much for listening to me and for tuning in. Thank you. Bye.